Okay. All right. So I already posted 2 sample final exams, and what I'm going to do is I will discuss most of the problems in the class here, and if you prepare for the final exam, you should, of course, you should go through all the material, but they'll pay more attention to the problems we discuss here in the class. Okay. So the first problem I want to talk about is we are given equation in 3-dimensional space. Okay. What we want to do is to find so this equation determines the surface, right? So find an equation for the tangent line, for the tangent plane, okay, to the surface at the point 1 and 1 and 1, and you check that this is indeed a point on the surface. Okay, this is surface and this is a point. Okay, so we have to find a plane. Right, so what we should know about that? Well, if you let the function to be x squared, 2y squared, 3z squared, okay, then the equation is actually is fx y z equals 6, right? And this is a level surface. The surface right now determined by this equation is a level surface of this function. So the surface, okay, the surface of the equation is the level surface of f. So gradient of f at that point is going to be the normal vector. It's perpendicular, at least, right? It's not necessarily unit vector, but it's perpendicular. Right? It's perpendicular to the surface, to the tangent plane, actually. Okay. So you get a gradient, right? Okay. So now, how to describe the all the points on the tangent plane? Take an arbitrary point x, y, z in the plane. You look at the vector, and this should be perpendicular. So right. So therefore, let's calculate the first. Okay. Let's calculate the gradient of f. The gradient of f at an arbitrary point is going to be 2x, 4y, 6z, right? Right, your partial derivatives. So the value will be 2, 4, 6. Okay. Then the difference of those 2 points give you the tangent vector, right? So the difference is, let's see, x, y, z, 1 and 1 and 1. So this is a tangent vector, okay? This gives you a tangent vector, okay? And then with a dot product of, of this should be equal to 0, right? So let's put the details here. The difference is going to be x minus 1, y minus 1, z minus 1, right? And here is 2, 4, 6. And then you write down the equation 2x minus 1 plus 4, y minus 1, 6, z minus 1 equals 0. So that is an equation. Okay. You don't need to simplify it. It looks fine. Okay. Okay. So remember, the gradient of function is going to be the vector perpendicular to surface. Okay, so here's a related topic. Okay, so consider the graph of okay. Consider this graph. Okay, then at the point x naught, y naught, z naught. So this one is going to be given by this function, right? So it is a point on the graph. So remember, okay, how to find this graph as a normal vector, okay? Okay, perpendicular to the graph at that particular point. There are two different ways to do. One is you view the graph as the level surface of some function. So you can let h, x, y, z to be z minus fxy, right? Okay. So then the graph is going to be, my God, let me see the function. Yeah. Okay, it's coming back. All right, so the graph is going to be the level surface of some function, okay? So you can use that to find the gradient. Okay, you let h, x, y, z to be z minus f of x, y. Okay, so if x, y, z is satisfying the equation, so z equals fx, y, if and only if is going to be 0. So the graph is a level surface, okay, of h. Okay, so that means the gradient of h, okay, is going to be perpendicular to the level surface, which is the graph. Okay. Okay. And if we compute it, it is going to be x, y, z, right? Yeah, there's 3 components here. It is going to be negative fx. Okay. Negative, right? And 1. Okay. When you differentiate the h with respect to z, then you get 1. So you get a number. You get a vector perpendicular to the level surface, which is a graph of function. That's one way you can do. Another way you can do is you parameterized the surface, the graph, using this, right? So then we know that this cross product, right, is going to be perpendicular to those two tangent vectors. Perpendicular to the tangent plane. Okay. At the point, okay, right? So if you look at the graph again, but you view it as a surface, then this is the R, right? X, and that will be the direction the derivative, partial derivative R with respect to y variable. Then the cross product will be perpendicular to those two vectors, of course, perpendicular to the tangent plane, because those are the tangent vectors. Then you just need to calculate this, right? Each of them. So what you get is ijk and 1, 0, fx, and 0 and 1, f1. And when you calculate this, you end up with, you end up with negative I minus j and plus k. Okay, so it's the same vector you will get. You will get the same vector. All right. My second problem is about iterated integrals. Okay, iterated integrals. Let's go over the formula. Suppose you have a domain in the xy plane. Okay, this is the D. If you project it to the x-axis is from A to B, right? If you project it to here is a C, and the highest point may be D. Okay, so the double integral of the function, okay, can be evaluated in two different ways. One is you fix an arbitrary point x. Okay, so x is between A and B. So you put a dx here. Then you draw vertical lines. Okay, you draw vertical lines, and you have to determine upper bound for the y variable, lower bound for the y variable. So this will be two functions depends on x and y, right? So here's fx dy. So this will be upper bound, but depends on x. Okay, so it could be no, we just use two functions depends on, yeah. So for the fixed, yeah, for each x between A and B, you have to determine the y value. So the y value, let's use g, okay? G and x and h and x, okay? If there's upper bound, lower bound, then you have a gx and hx, okay? So we never see something, you cannot interchange the order quick, you know. So the integral, all side integral, the upper bound, lower bound must be numbers, never be a variable, okay? Now, if you want to use the y variable first, then for an arbitrary y variable from between C and D, right? This will be dy. Then you have to draw a horizontal line. So this horizontal line gives you the range for the x variable, okay? So we have to figure out what is that, right? For each y between C and D, you have to figure out the x variable. If the x variable, you know, if you have yeah, depends on y, right? So you can use other functions. I'm going to say use phi of y and less than c, right? Okay, so you have two functions, okay, and then you put phi y, okay, and here's fx, y, and dx. So this is how do we set up two iterated integrals, okay? Now, sometimes you are given the iterated integral, so you have to figure out the domain first, go through the double integral, then you get to the other one, okay? So if you have, if you are given Okay, if you're given this, okay, what does that mean? Step one, you have to figure out what is the double integral of the function. So you have to figure out what is d. Okay, what is d? Clearly, from here it says for each y between 0 and 2, the x variable is between 0 and y squared, right? Yeah, so you retain, and it's y squared, okay? So how do you describe this d? You draw the picture here. That's what I want to see. Then you have a question, why have to draw the picture? This is part of the solution. Okay, you cannot skip it. Okay, so y is between 0 and 2. Okay, and for each y, x is also start from here. And then the other side will be x equals y squared, right? So when the y changes, x changes. So this is going to be like that, part of the parabola. Okay, so this point when y is 2, x is 4. Okay, that will be the end point. So you get a bunch of horizontal line segments that filled up this domain. So that is a domain. Okay, that is the domain. So this is a D. So you have to describe the domain. Then you can, once you know the domain, then you can exchange the order, right? So here, this is going to be 4. Okay. Now, some students, without understanding the problem, just say, I'm going to interchange that. This tells me you totally don't understand what is the iterated integral. Okay. You just exchange the order. Okay. So that tells me you knew nothing. Okay. First of all, the y variable should be, on the left side of the integral. Okay. The integral on the left side. Okay. So what you have to do is you have to look at the picture for each x between 4 and 0. So the y variable, the upper bound for the y variable, look at this 2, right? So you have to figure out what is 2. Yeah. The y variable, the lower bound for y variable is determined by the equation, relationship x equals y squared. But you have to solve for y in terms of x as a square of x. Okay, so that's going to be the integral, right? And square of x and 2. Okay, it's going to be, this is going to be the y variable, yeah, and the dx. Okay. Okay. Our next problem, I want to evaluate this triple integral. Okay. So E is determined by the seeing coordinates, y between 0 and 1, x is between 0 and, there's order here, y first, then x, then z. Z is between 0 and x. Okay, that's actually, it's described one by one. So for each y between 0 and 1, x is between 0 and the square root of 1 minus x. Then z, based on x and y, you get lower bound for z, upper bound for x, lower upper bound for z, lower bound and upper bound for z. But this time, z depends on x only, the upper bound, right? All right. So how do we set up as a iterate? We have to set up an iterated integral to solve this triple integral. Okay. Okay. So this d, okay, you can write down directly, right? That's the idea, you know. So y is between 0 and 1. Okay, y is between 0 and 1. So that's dy. And for each y variable, x is between 0 and this, and put dx here, right? Then for each x and y, z is between 0 and x. Okay. So this will be this will be 2y here dz. Okay. Okay, that's the one way you can do. And you can also describe the e in a different way. Okay. Okay. You can also describe the e in several ways. So, like for example, e I can describe it in this following way. Okay. And for x and y in d, and for each x and y in d, z is between 0 and x. Okay. So that means this is a d, okay? So for each d, you have you have a lower bound for the z for every point x and y in the d, okay? Z is between 0 and x. So, and what is d? D is again described as two inequality, okay? D is described by this two inequality. X is y is between 0 and 1, x is between 0 and you can do step by step. Okay, so this, if you do like this, then you can have a double integral first, and z is from 0 to x, 2y, dz, and dA. You can do step by step. Okay, it's the same. Okay, you get double integral first. Okay, so now you will get 2xy. Actually, is a 2x. Yeah, the antiderivative yz is between us 2xy. Okay. All right, then you change the double integral to an iterated integral, because for each y value from between 0 and 1, right? The x value, x is between 0 and something here. Okay, so the relation between x, right, so x is equal to square root of 1 minus x squared. So x is x squared plus y squared equals 1. This is a portion of the circle. Okay, so you have this is the integral on the circle in the first quadrant. Now you have two different ways to evaluate. You can do it directly, right? Okay, and that will be 2xy dx dy. Antiderivative of this will be x squared y. Now we are lucky here, we can, right? Then you replace x squared by 1 minus y squared. Okay, so you will get y minus y cubed dy. Okay. Okay. So it will be half of y squared minus a quarter of y to the fourth power. Evaluate at 2 endpoints, it's 1/2 and minus a quarter, so it's going to be 1/4. Okay. If you see that this is if you see this is it's a portion of the circle, you can use the polar coordinates to evaluate the integral. You don't need to go through the iterated integral. Sometimes you cannot do it. It's too complicated. So you can use polar coordinates. It's r cosine theta, y equals r sine theta. Okay, r is between 0 and 1, theta is between 0 and pi over 2. Okay, so that will be the integral from 0 to 1, from 0 to pi over 2, and the twice of xy, right? xy, so it's cosine theta, sine theta, and then times r, and the d theta dr, okay? Right? This r coming from the change of coordinates. Okay, so what they can do, it's a little bit complicated here, right? 2 cosine theta sine theta will be sine 2 theta. So the antiderivative of sine 2 theta will be negative cosine 2 theta divided by 2. Okay, so you plug them into what do you get here? You get negative 1 over 2, negative, right? Minus is a plus. Okay, so the answer is 1. So you just need to evaluate r cubed, and then this will be a quarter. Okay, yeah, you get the same answer, but just different way to evaluate. Right. So that's about triple integral. Triple integral evaluate using the triple integral evaluate using iterated integrals. Okay, you can step by step. You can do it one time. You know, you can write down 3 integrals. You can also write down 2 integrals. One is a double integral. Okay. All right. Yeah, we can. In the last class, we can do more exercise about this. Let me go through the problems here first. So this is a line integral on a curve. C is described by the following parametric questions. Okay, T is between 0 and 1. All right, this is an easy one. Okay, because you can change it to, so what is ds, right? ds is going to be x prime t squared, y prime t squared dt. Okay, if you know that part, then that will be, that would be 1 squared plus t, right? Partial derivative of that, t squared dt. Okay. All right, so now this integral of the function around the curve can be the integral between 0 and 1 with respect to t. So what is x? X is t. Then you use substitution. Okay, you let 1 plus t squared and du equals 2t dt, and then for the new variable, right? When t equals 0, you get 1. When t equals 1, you get 2. And this is u to the 1/2. T times dt is half of du. Okay. Then you find the antiderivative of this function. Antiderivative of this function is 2 over 3 u to the 3 over 2. Evaluate 2 endpoints. Okay. So you got 1/3 and 2 to the 3 over 2 minus 1 to the 3 over 2. So that's it. Okay. So you have to use substitution to evaluate. This is not a complicated problem. All right. Our next problem will be, you are given 3 points. And you find the vector perpendicular to the plane through this point, and find the area of this triangle. Okay, this is a special surface actually. Okay, so given 3 points, PQ, okay, and R in the space. So these 3 points, you know, it's hard to draw it, okay? And maybe P is here, you know, Q is somewhere here, I is somewhere there, okay? I just draw like that, okay, in this space, okay? Yeah, it's hard to look at. So P, Q, and R. What we want to do is we want to find a vector perpendicular to this plane, okay? To this is a surface in space, okay? You can also find a parametric transition for this surface, okay? And find the so how do you find the area of surface? Find the area of surface. Okay. Now, without using calculus, you still can do that. The idea is as follows. Okay. So if this is a vector u, that is a vector v. Okay. Then u cross v is a perpendicular to the plane. That's the first thing, right? Second, half of the length of this is going to be the area of the triangle. Okay, actually, the length of the cross product is going to be the area of the parallelogram. Yeah, the length of the parallelogram. The reason is the cross product is going to be, look at that, right? If this angle is theta, so the cross product actually gives the length of u times the length of v times sine theta. Okay, so v sine theta is, hold on, the v sine theta gives the height of the parallelogram. Think about this. This is a u, this is a v. It's this gives you the v, this is length, right? It's sine theta. So the height times the base gives the area of the parallelogram, but the area of the triangle will be half of that, right? So you don't need to use calculus to solve the problem. Okay. Actually, we want to parametric, yeah. So if you want to find the parametrization for this plane, okay. Okay, let's finish this first, okay. So the u, how to get a u? U is the difference of those 2 points r, right? -1, 3, 2, minus 1, -2, and 1, right? So the answer will be -2 and the 5, 2 minus 1, okay? And the v is going to be q minus, right? Q minus the point, okay? So you will get 3, 4, and 0, okay? Then the cross product is going to be ijk, okay? So you can -2 and the 5, 1, and the 3, 4, and 0. Okay. So you end up with -4, right? Yeah, let's do the quick. Plus 3j. The last one will be -8 minus 15. So it's going to be -22. Okay. Yeah, so you can, so this is a vector perpendicular to U and V, of course, perpendicular to the triangle spanned by these two vectors. Okay, so the area of the triangle will be half of -4 square plus 3 square plus -23 square. Okay, so that's it. Okay, now I want to do a little bit more about this. How to find parametric equations for this surface. This is special surface plane. Okay, so you can parameterization. You can find like that. And you can use U and V. Okay, and that is going to be. See, look at this. Okay, that's U. That's a V. Okay, and the arbitrary point here. Okay, is going to be like that, right? This is the origin. How to describe it? First, you use this vector, right? Then use that vector and add them together. And that vectors can be combination of these two vectors, U and V. So that would be the vector from this. What is it? This is a P, right? So the component, yeah, P. The vector P is 1, -2, and 1. Okay, and plus, and the U, the vector U, right? So the vector U we got here is -2, 5, 1, and the vector V, 3, 4, and 0. Okay, so you can add them together. You can get the 1 minus 2U plus 3V, and -2 plus 5U plus 4V, and the 1 plus U. Okay, so you have yeah, this is a parameterization for the plane spanned by those two vectors. Okay, so you get parameterization, and you can use a parameterization to find the area of that surface, which is the plane. Okay, so I'm not going to continue to do this. All right, so let's try a different problem. Okay, this is about the limit of a function. Okay, I hope you still remember, right? How to find the limit of this function. All right, I look at this, right? The numerator, the degree of the numerator is going to be 3. It's greater than the degree of the denominator, which is 2. So I think the numerator approaches 0 faster than the denominator. So I'm pretty sure this is going to be the limit is going to be 0. The question is, how do you prove it? If you take an arbitrary line, that's not the proof actually. Okay, for any arbitrary line going through the origin, this is the limit is going to be 0. Okay, so let's take a look at this. So I draw the line, arbitrary line. Okay, the arbitrary line would be x equals at, y equals bt. I do not fix a and b. Okay, so I want to, so t approaches 0, then the points on the line approaches 0, right? Approaches the origin. So x, y approaches 0, 0 as t approaches 0. Okay, So it's equivalent, but that approaches it along the line. So then x squared y, or x squared plus y squared equals, that is going to be a squared b, right, t cubed. So a squared plus b squared and t squared. So you get a squared b, a squared plus b squared, and t. So clearly this approaches 0, right? Now the question is, you can only say conjecture this is a limit is 0, but that's not the argument, correct argument. So we can only conjecture that, right? So limit xy approaches 0, but that's not the original definition, okay? We can only conjecture this is going to be 0. But the above argument is almost the proof, but it's not the concrete proof, because in mathematics, when we say xy approaches 0, I do not specify it approaches 0 along the line. It approaches 0 from all the directions randomly, okay? So this is origin. There could be any, yeah. Here, there, eventually approaches 0, right? So it's not necessarily along the line. It could be like, like the Milky Way, going rotate, going to that, right? So how can you show this is also, if the point approaches the origin along this curve, right? Can you still show that this limit is 0? No. So the best way to do is we need the following inequality. This is very useful equality, okay? And so therefore, x squared y. Now this expression can be negative, can be positive. So I put absolute value here. So I take x here and x times y. So x times y absolute value is going to be less than or equal to 1/2 So this cancels out. So this will be half of absolute x. All right. Of course, this can be also written as less than half of the x squared plus y squared. You can make it large. Okay. So when we say xy approaches 0, 0, if and only if x squared plus y squared, this approaches, this is equivalence. Okay. So clearly, so therefore, x squared y approaches 0 as x squared plus y squared approaches 0 by this inequality. Okay, so we are done. Right, because the absolute value of the functions has upper bound, and x squared plus y squared approaches 0, then that forces, that forces this expression approaches 0. Okay. Right. Our next problem is evaluate the integral of the line integral at C, along the C. Now, what is f? F is going to be y squared I, z squared j, x squared k. Okay. C is a triangle. Okay. It's a triangle. Oriented using this order of the coordinates. Okay. So if you use so here's the point. That's another point. That's another point. So go in that direction. Okay. So we want to evaluate this integral. And the line integral. This is a closed line integral. Okay, it's closed. So if the curve is closed, so there's a chance you can use a Stokes theorem. Okay, convert it to a double integral instead of line integral. Okay, because if it's do the line integral directly, you have to find the parameterization for 3 pieces of the curve. Okay, and it can be done, but it's more complicated than you thought. Okay, so if you use by Stokes theorem, okay, so this is surface, right? This integral. But you say, how do I know I can use a Stokes theorem? But well, as long as the curve is closed, then it includes the surface. Okay, then you should think about maybe you can use a Stokes theorem. Okay, so this will be the double integral S and the curl of the vector field and ds. Okay, so you need to know the normal vector. Okay, the normal vector will be this one, right? I think a couple things have to do. Find the normal vector. But for the triangle, the normal vector is obvious. It's going to be 1 and 1, and when you normalize it, it's going to be 1 over square root 3. Yes. So you should look at the statement of the Stokes theorem. Okay, Stokes theorem is used for the closed curve. Okay, not a closed surface. Okay. So the Stokes theorem says there's one side, it's a closed curve. One side is a line integral, other side will be the surface integral. Okay, the surface is spanned by this curve. So there could be any surface. Okay, as long as the boundaries of the given curve. Okay. Yeah. Okay. So now you have to compute the curl, right? The curl of the vector field. Okay, so let's compute the curl of vector field. Hold on. My screen is yeah. Okay, freeze. Okay, now this works. All right, so let's compute it. So I, J, and K. Now this surface is a triangle. So the surface integral probably will be a simple, okay? So then you compute this. Let's see, what do you get here? You got negative 2z I minus 2xj minus 2yk. Okay, so you can find out this. Okay. So now the surface integral S okay, it will be the integral negative 2z vector, right, negative 2y, the dot product 1 and the 1 and the 1 and the ds, okay? And then you multiply this out, it's negative 2 over square root 3 And here is be z plus x plus y ds. The problem is, are we lucky here? Actually, we're very lucky here. Okay, z plus x plus y is going to be constant over that triangle. The reason is the equation for this plane is x plus y plus z equals 1. Okay, right. For this plane. Now, if it's not right, if it's a surface, you have to find the parametrization to evaluate the surface integral. But here we're just lucky. This is determined by the equation. So the value of z plus x plus y on the surface, on the triangle, is always equal to 1. So that's why this is going to be the integral of this. And that is the area of the triangle. Area of the triangle. Okay. Area of this triangle. The question is, how can I find the triangle? Area of the triangle. This is iterated. This is square 2, right? So if we have a equilateral triangle, can you find the area of this? And that is a geometry you learned in middle school, right? So how do you do that? This is all the angles at 60 degrees, right? Okay, so first of all, you find the height of the triangle, h, and the h should be equal to square root over 2 times square root 2, right? Right, because it's 60 degrees. Then once you find the h, then you can find the area, right? So it's negative 2 over square root 3, and the 1/2, the base is 2 square root 2. The height is going to be this. This is the height. So we have so many numbers here, right? And the answer will be just negative 1. Okay. Now, if the surface is not so special, then how do you evaluate the surface integral? Well, you have to parameterize the surface, then use a formula, right, to evaluate, the surface integral. Okay, and for general surface, yeah, we will probably see this problem here. If we have a parameterization u and the v, right, and ds is going to be dA, right? Okay, ds du dv. Okay, and ds, this is the area element. dA. Okay. Okay. So now let's evaluate this integral here, x squared plus 2xy and dx x squared y dy. Okay, C is a path from 0, 1 to 1, 2. Okay. Now you also have to show that the integral is independent of path, okay, from between those 2 points. So that already implies that the vector field you are going to get is a conservative. So you don't need to evaluate this integral directly. You just need to find a function. Okay. Yeah, we know that if f equals greater than r, right? So then then for any, right, this is going to be fq minus fp, okay, for any curve p and q, okay. Okay. So then it's independent paths. So all I have to do is just find the gradient of some function. Okay. So you will get okay. So you're trying to evaluate, find this f. Well, because you're told that this integral will be independent paths, so it should be the gradient, the vector field is gradient function. So you should be able to solve it. Okay. You can use the second equation or use the first equation, doesn't matter. So if you use the second equation, it's dy, right? And plus constant. So you will get the integral of x squared dy. So it's x squared y plus cx. Okay. Then you differentiate with respect to x. You get 2xy and c prime x. And that's supposed to be x squared plus 2xy. So c prime x is going to be x squared. Okay. Then cx is going to be 1/3 of x cubed. Okay. You don't need to write plus constant here, it's just one special. So you get function, you get 1/3 x cubed plus x squared y. Now that is a function for the, yeah, this is a function. Okay, the gradient of the function is a vector field. Okay, so therefore, this line integral we are given is going to be the value of the function at the two end point. And I think it's 1, 2 minus 1. Oh, I forgot. What is that number? Yeah, 0, 1. Yeah, 1 and 2. Okay. So just evaluate the function at these two end points minus okay. So the answer will be 1/3 plus 2. That's going to be 7/3. All right. All right. So this example shows you that that's the easy way to evaluate the line integral. Okay. If the function is a gradient of another, if the vector field is gradient of some function. All right. All right, let's take a look at another example. Okay. So now evaluate this surface integral x times y ds. Okay, that's surface integral. X, S is a part of the plane. X plus 2y plus z equals 2. It's that lies in the first octant. Okay, so this is a triangle. Just simply say the triangle passing through the 3 points. Okay, so when the y is 0, that's going to be 2, right? And this would be 1. And this would be 2. So this is a triangle, okay? So that is a surface. Now, how do you evaluate a surface integral? Okay, how do you evaluate a surface integral? Now, you view this surface as a graph of function, okay? As a graph of function. So you get, so you actually, yeah, we already did, so if the graph of function, so z equals 2 minus x minus 2y, this is my fx, right? Right? Yeah. So we already know for the graph, ds is going to be fx squared plus fy squared plus 1 dA, okay? ds dx dy, okay? So you can, this is a domain D, okay? So the surface integral will be the double integral of D. Okay, what is a D? D is, and here's 2, here's 1. So that is a D, right? You view the triangle as a graph of the function over this D. Then ds is going to be this, okay? This can be calculated, right? You can, yeah, this actually comes from the norm of the cross product of some two vectors, tangent vectors. Okay, so this surface integral x times y ds is going to be the double integral, still x times y, not be changed. Okay, and this will be the gradient of it's the fx. That's a partial derivative. The first one is -1, and that will be -2 squared and the +1 and the dx. So that would be 1 + 4 + 1 is 6, square of 6. Okay. Then you just need to focus on the double integral. The double integral for each x between 0 and 2, right? What is the lower bound for the y? It's 0. What is the upper bound for the y? For the upper bound for the y, because this is well, let's find out the equation for this. The equation for this will be x plus 2y = 2. Okay, so when y = 0, x is 2. When y 0, x is 2. When x = 0, y is 1. Okay, so that is going to be the upper bound for the y will be 2 minus x divided by 2. Okay. All right, so x is between 0 and 2 dx, y is between 0 and, okay. So the antiderivative of x times y with respect to y is half of y squared and x. Okay. So we x, y squared, half of 2 minus x squared dx. Okay. All right, so you get a polynomial. So you can evaluate this polynomial. Okay. Question is, how do you do that? Right? You can evaluate, right? So you can take 2 out, that'll be square root of 6 over 8 now, 4 squared. So you get x, 4 minus 4x plus x squared dx. Okay, let's find the antiderivative of this. 4x squared, x cubed. So the antiderivative will be 2x squared, 4 over 3x cubed, a quarter of x to the 4th power. Evaluate the endpoints. Then I get, yeah, this is going to be 8. This is 4 times 8 divided by 3. This will be, 2 to the 4th power over 4. So this can be simplified a little bit. Okay, so 16. Yeah, this is just 4. I can take a 4 out. Yeah, make it a little bit simpler. I take a 4 out. 8 divided by 4 divided by 8 is 2. So it's 2 minus. Yeah, okay. So it'll be 3. 3 minus 8 over 3 will be 1 over 3. Okay, so that will be the answer. Okay, you can complete the computation, right? No problem. Now, what else we should do? Okay. Our next problem is let's find the angle between 2 planes. This is not a very common problem. between the planes. 2x minus 2y plus z equals 1, x minus 2y plus 2z equals 0. Now, how do you find the angle between the two planes? So you draw the two planes. Okay, that's an intersection here. So this will be the angle, right? Right, this will be the angle. But how can I find the angle? Well, we will use the normal vector. Okay, you look at this cross section. Okay, you want to find the angle, right? So let's take a look at this two normal vectors. The normal vector to this line, the normal vector to this. I think this is the same angle here, right? Okay. Then you say, well, the normal vector could be, we don't know the orientation. It could be, it could be in the opposite direction. Okay. So this could be in that direction. So then you get another angle, which is beta. But that angle is also can be viewed as the angle between those two lines. Okay, this can be beta, right? Right. Okay, so this is another angle. If you want to look for angle less than pi over 2, yeah, you will see that, right? So there's a small difference. All you have to do is find the normal vector to each plane. The first plane, the normal vector, is going to be 2, -2, and 1. The normal vector for the second one, just so you can read them from the coefficients of the equation. Right? Right. So then the inner product, okay, divided by the length, is going to be the angle between them, between those two normal vectors. So the inner product, first of all, let's look at the inner product. Inner product is going to be 2 times 1 plus -2 times -2. And the plus 1 times 2. Okay, then the length of the N1 will be 2 squared plus -2 squared plus 1 squared. And here's 1 squared plus -2 squared plus 2 squared, which is 2 plus 4 plus 2. And here's the denominator is going to be, I think it's going to be 9 here, square of 9. Okay. So when you compute it, it's going to be 8 over 9, which is smaller than 1, clear. If it's larger than 1, some computation there, mistakes there. So theta will be arc cosine 8 over 9, sorry, 8 over 9. So 8 over 9. Okay, that's it. This is the angle between 0 and pi over 2. Okay, it's between 0 and pi over 2. Okay. All right, yeah, let's look at the next problem. Find this is evaluate this surface integral. Evaluate this surface integral S dx. Right? So F is going to be x squared I yj plus zk. Now S is the surface, right, of the solid bounded by, so that means it's closed surface, okay? bounded by the cylinder x squared plus y squared equals 1, and the planes. I think we discussed this problem before. Okay, first of all, you draw the graph, okay? You draw the graph, and yeah, first of all, you draw the graph, okay? So this is a cylinder, okay? X, Y, Z here. So this is a unique cylinder. Okay. So Z is X equals Y. I think it's never been negative, but Z will be 0 on the other side when X equals -1. When X equals positive, when Z is on this 2. So the plane will be cut through like that. Okay. So this is the solid inside. Now, the surface consists of 3 pieces. One is a portion of the cylinder. One other one is the disk at the bottom. Other one is an elliptic, right? Elliptic surface, as on the plane. So if you want to evaluate this surface integral directly, then you have to evaluate the surface integral over 3 surfaces. And then you have to parameterize surface. It's too complicated, right? It's too complicated. So what they did is, this is so you just by the divergence theorem. Okay? By the divergence theorem, okay, you will get, right? Remember, right? This is surface integral ds, right? This is will be triple integral divergence of f and dv. Okay, using that, then you can quickly evaluate this integral. Okay, so you calculate the divergence. This is the divergence is going to be partial derivative of x squared. It's 2x, right? Plus 1, plus 1. Okay, the divergence of vector field. The vector field is very simple, x squared. And 3 component x squared y z. Okay. And so you get this. Then it's a triple integral, right? So you have to change it to the iterated integral. The iterated is a disk d. So for this is d, right? D is going to be x squared plus y squared less than equal to 1, right? For each point x, y in the d, the z value is between 0 and x plus 1, right? You know, this is how to, right? So this is going to be the double integral. Z is x plus 1 here, dz. And dA is area amount of the d, right? So now, antiderivative 2x plus 1, 2 and x plus 1, right? And then dz is gone, right? So then this is x plus 1. I take a 2 out there. It's x squared plus 2x plus 1 dA. Since this is a disk, so it's natural to use a polar coordinate. Okay, so if you use a polar coordinate, this is a 1, and here's from 0 to 2 pi. X is r squared cosine squared theta, 2 cosine theta, r, and plus 1, and d theta, dr. Okay, now the integral of this term is going to be 0. The integral of cosine square theta is 1 plus cosine 2 theta, okay? Right? Yeah. So the integral of okay, this r squared here. The integral of 1/2, okay, over the integral is 2 pi. Integral of cosine 2 theta will be 0. Integral of cosine theta will be 0. So the last one is integral 1. That gets 2 pi. Okay. So you can get this. Then I take a pi out. I get r squared plus 2 NTR. So the antiderivative is going to be this. Okay, you plug them into the formula. Okay, then you get the answer. Okay. Do I need to multiply by r? You're right. No, polar coordinates. It's r here. I missed. That's my mistakes. Okay. Okay. So I get r cubed and r. Yes, you're right. It's easy to make mistakes. Okay. Okay. Let me finish it quick. We finished 11 problems within 1 hour, 15 minutes. Okay. So the antiderivative of this function is a quarter of r to the 4th power. It's r squared, 0 to 1. Okay. So it'll be 5 pi over 2. Okay. So that is today's class. We'll continue next time.